Previously we had talked about how if we had a low intensity laser beam or light source incident on a double slit, you would see one little dot at a time appear on a screen beyond the slits. So here's your laser beam coming along, and it's passing through the slits, and if the intensity of that laser beam is low enough so that you might think of one photon at a time traveling through these slits to the screen, you would see one little dot appear at a time. One little dot, and then another little dot, and then another little dot, and another little dot. And over time, as you collected these dots, you found that there are certain regions on the screen where the density of the dots is higher, and other regions where the density of dots is lower. And so, after thinking about this, we concluded that the pattern of densities of dots is exactly the same as the brightness pattern of a higher intensity beam. In other words, a beam that has a bunch of photons that pass through a bunch of them at once. You see a bunch of light on the screen. You can't really make out individual dots. You just see big bright spots. And so these dots that you end up seeing when the beam is low in intensity is each individual photon hitting the screen. And over time, the pattern of those dots builds up into that pattern that you saw with the high intensity light source, where you couldn't see the individual dots. And so by thinking about wave theory, thinking about light as a wave, those bright spots that we see on the screen when we aren't seeing the individual dots, those bright spots can be described by thinking about wave interference. And the intensity of these bright spots is related to the square of the amplitude of the wave. So we had that intensity of the bright spots was proportional to the amplitude squared of the wave. And so when we talked about light, we said, well, light's an electric field, and what's happening is that there's sort of, in a sense, electric field at a point on the screen due to stuff coming out of this top slit as well as stuff coming out of the bottom slit. Those electric fields are adding together at these bright spots, and it's that adding together that gives you a larger amplitude of the wave at the bright spots, and therefore a larger intensity. But you're adding electric fields together to get the amplitude, and then you're squaring that. So you're adding electric fields and squaring that sum of electric fields to get the amplitude squared. And so the higher the amplitude, the bigger the intensity. Thinking about this in terms of going back to the individual photons traveling through the screen, through the slits, the density of those spots is proportional to the intensity. So the more dense the spots are, those would be locations where the intensity is high. And so we can say that this intensity is also related to the density of spots. And then all we really know then about thinking about where the next photon is going to go, if you have a low intensity laser beam with one photon at a time going through here, we cannot say anything about exactly where that photon is going to land. Is it going to land here, here, here? We don't know. But we can say that there's some probability that it's going to land in certain places, and that probability is proportional to the density of the spots that are already there. In other words, it's proportional to the intensity of the spots, in a sense, or it's proportional to the amplitude squared. So ultimately, we had talked about this equation where we can write that probability is proportional to the amplitude squared. So there's some wave, for the example, or in the example of light, the wave is an electromagnetic wave, so the amplitude is the size of the electric field. If you square that, that is what's proportional to the probability of where the next photon is going to land, or the probability of finding photons. So a higher amplitude means you have a higher probability of finding photons having hit that location on the screen. So now when we think about electrons or other particles that might have mass, we can do the same experiment and we find the same results. And that is that we send electrons through the slits, and electrons individually land at different locations, seemingly random locations on the screen. But over time, as we record where these electrons land, we find that they land in places that that are kind of dictated, in a sense, by the wave, some kind of a wave that's associated with these electrons, in such a way that the higher the intensity of that wave, the higher the amplitude squared of that wave, the greater the probability that the electron would land at that location. In other words, if we send a beam of electrons in that has a lot of electrons, we don't see individual dots appear one at a time because there's just so many hitting the screen at one time. We see big bright spots, just like we do for light. And we can talk about the intensity of those bright spots. And the intensity of those bright spots is then proportional to the probability of the next electron coming through and hitting a certain location. So the next electron coming through and hitting right here is a pretty high probability. Right here is a pretty low probability. Right here is a very high probability, and here is low, and here is high, and so on. So again, the intensity of the pattern that we see when we have a lot of electrons going through, and what we see looks very much like wave behavior, that intensity is proportional to probability of finding an electron, or an electron having already hit the screen, or the probability of where the next electron would hit the screen. And so, you know, we see some wave behavior, so there must be some kind of a wave that is associated with these electrons. And if that's the case, then that amplitude of that wave squared must be what's related to probability of finding the electrons. So instead of an electric field, though, this wave is a little bit different. We're not quite sure exactly what to make of it. We're just going to give it a different symbol, psi. And so we say that this amplitude squared is, really we're going to call it psi squared. And run into space. So psi squared is what we're going to ultimately calculate. So this is why we're interested in calculating this wave function and then squaring it. We don't care too much about the wave function itself. What we ultimately really care about is the square of this wave function. But we have to find the wave function first. And so that's the way we get this wave function, is by solving a differential equation that governs these wave functions. In much the same way as how we would get an electric field, we would solve some kind of equation that governs how electric fields are created, or how they propagate, or how they change, and things like that. So probability of finding a particle in a certain region of space is proportional to the amplitude squared of some kind of a wave that represents that particle. And for matter waves, we're just going to call this thing the wave function psi. For light waves, it's an electric field. For matter waves, for matter, it's something different. We're just going to give it a name, call it the wave function, call it psi. But what other kinds of things could probability be related to? We're just saying that the probability of finding a particle in a certain region of space, the probability of finding an electron hitting the screen here or here or here, it's proportional to the size of this wave function squared. Well, are there other things that the probability could be proportional to as well? We'd like to have an equation ultimately that allows us to calculate probability. So let's go on the next screen. We'll kind of draw an example wave function, just kind of a quick little wave function that isn't for any specific problem. Just make a graph of something, say that it's a wave function, and then we'll talk about some of its properties and how it's related to probability. So suppose we have a wave function that looks like this. Previously we had said that these wave functions are generally complex things. They have a square root of -1 in them. Let's just suppose we're looking at the magnitude of this wave function. In other words, we're looking at the wave function squared. And so let me actually put that here. If we're looking at the wave function squared, that thing is a real thing. Oops. And that thing is a function of x, as well as a function of t. And so I've got drawn here a graph that's a function of x at some particular time. It could be time equals 0. And so, you know, I don't know what problem this graph really represents. Doesn't matter. This is just some function of x. And if it is a wave function for a particle, what this means is that this particular region on the x-axis, this is for a particle that is somewhere on the x-axis. This wave function is a function of x, representing some particle that's on the x-axis, moving horizontally, moving along the x-axis. So it's a one-dimensional problem. Having a graph like this means that where the wave function squared is large, there's a high probability of finding the particle there. In other words, on the x-axis, somewhere in this region, there's a high probability of finding the particle. and this wave function squared has some value, whatever that is. You could kind of trace this over to the vertical axis and read off some value. What are the units of that? What is this? It's not distance, probably. Ultimately it's related to probability. But anyway, when you have a graph like this of a wave function squared, the couple things that are important to remember is that, one, when you see that the graph is sort of tall, that has nothing to do with any vertical motion of the particle. This has nothing to do with the particle moving up and down or anything like that. This is simply a graph of probability, in a sense, meaning that along the axis in this region here, the probability is large of finding the particle. So there's some particle somewhere. You don't know exactly where it is, but this wave function represents probability of finding it. Over here, as you get larger values of x, or more negative values of x, according to this function at least, the probability is lower, much lower, that you would find the particle. So wave function squared is proportional to probability. When it's large, probability is large. Well, let's look at a region of space here in the middle of that graph. So somewhere in this region here. So between this value of x and this value of x. If we look at that region right there, that region has a width, maybe we could call it delta x. Or if you want to think about it being infinitesimally small, you could write something like dx, some infinitesimally small distance. There's some width in that region. And if we look at the probability in that region, it looks, at least in this example, it looks nearly constant. If you look across this, look at this graph across this region here, that probability graph is more or less constant. Okay. So the wave function squared has a certain value there. Probability has a certain value there. So probability is proportional to wave function squared, and so probability is proportional to whatever this number is. Now, if I were to double my distance, suppose I made this width here twice as big. In other words, I looked at this region here. I looked at this entire region here. So that would be something like 2 delta x. The original delta x that I chose is smaller. This bigger region is like 2 delta x. Do I have a higher or lower probability, or is it the same probability of finding the particle in this small region versus in this region twice the size? If the wave function squared has the same value roughly in that entire region, so the wave function squared has one number, there's one number associated with it. The function here that I've got drawn is pretty much constant across this region. That probability, the wave function squared, is just some number. Is the probability of finding the particle across this small region of space the same as finding it across the bigger region of space? And the answer is no. The more region of space you look at, the higher the probability that you're going to find the particle. In the extreme case, if you looked for the particle sort of anywhere on the x-axis, you're going to find it. It's somewhere on the x-axis. If you only focused your attention on a very small region of the x-axis, there might be some probability you're going to find it there, but it's going to be much smaller than if you had looked over a much larger region on the x-axis. So probability, yes, it's proportional to wave function squared, but it's also proportional to the amount of distance that you're looking at. So it's proportional to two things, the wave function squared times the distance. So we can write down something else that's called, not probability, but it's called the probability density. Probability density is really what we're referring to when we say wave function squared. Because to get probability, you multiply the probability density by a distance. And we'll just use an infinitesimal distance, because technically the wave function could be changing very rapidly, so you have to really zoom in on a region of space that's small enough so that the wave function is more or less constant over that region to be able to say that probability is the wave function times distance. Okay. It's sort of like the word density here is a little bit strange. Maybe you think about density as being something divided by volume, and it can be. It's just that we're talking right now at least about a one-dimensional problem, a particle that's moving only on the x-axis, and so it's only moving in the x direction, not in the y or the z. So our wave functions are only functions of x, and so we only multiply them by a distance rather than an area or a volume. We still use the word density. So probability density is the wave function squared. It's just the name that we give it because we have to multiply this thing by something else to get probability. We have to multiply it by a distance. And we do this because we know that probability isn't just proportional to the wave function squared, but it's also proportional to the distance. Again, if I have these two regions of space and the wave function is roughly the same across the whole region, certainly the probability of finding the particle is going to be about twice as big across the whole region as it is across just the small first half of the region. Probability depends on distance as well as wave function squared. So probability of finding a particle is the wave function squared times a small distance. And again, we put a small distance in there, dx, in there, because technically we have to focus on, to make this equation sort of valid, this probability equals thing valid, we have to be thinking about the wave function having some constant value over this distance. And that's only true in general if the distance is very small. Okay. So this is kind of like things from Physics 1 when you talked about work done. When forces do work, you might have written down an equation that work equals force times distance. Force times distance. Let me just erase that. Force times x or something, for example. Force times x. Well, that's only true. Force times distance is only valid if the force is constant and the distance is, a straight line, basically. If you're talking about work over a distance and the force could be changing quite a bit, you have to focus on small regions of space over which the force is roughly constant and talk about work being F times a small distance, dx. And then you end up doing an integral. You add up all these products of force times distance to get the total work done. In the same sense, what we'll be doing is we'll be looking at taking the wave function squared, multiplying it by distance to get probability of finding a particle in that small region of space, and then we add up all those probabilities to get total probability. Okay. So, in a sense, this word probability right here should be like an infinitesimal probability, because I'm multiplying my density by an infinitesimal distance. Ultimately, what we'll find is that we'll have an equation for probability that involves an integral, and we can write that as capital P for probability equals some integral of the wave function squared times dx. And we'll have certain limits on this integral from some number a to some number b, depending on what big finite larger region of space we're actually concerned about. So these wave functions are going to be important. We'll have an equation, the Schrodinger equation, to be able to solve for these wave functions, and then once we have these wave functions, we'll be able to calculate things like probability of finding a particle in certain regions of space. And so we'll do a bunch of different examples eventually on how we do all that.